So I would like to thank the organizers for the invitation. It's great to be back. I spent 3 years here as a postdoc. I apologize for the voice, but this is joint work with Igor and Greta Panova. So I mean, here I just have this picture of IPAM and these two other buildings, this data center and the Guggenheim, and they're related because actually the same architect did all of them. But then let's talk about Schubert polynomials, and we'll see how they're related to plane partitions and to ASMs to get some bounds. Okay, so I'll talk about Schubert polynomials and some a combinatorial model to encode them. We're going to talk mainly about specialization, so counting how many monomials it has, and what's the maximum value that this attains. Some special cases, and then progress on some conjectures. Okay, so W, I'll write it as a permutation in one-line notation. And we saw it this morning in the talk. We saw Schubert polynomials. We're going to index them by the permutations. So these are certain polynomials in non-negative coefficients. And they were defined, as we heard this morning, by Lascaux and Schutzenberger in the 80s to study Schubert varieties. And it's very, very important, for example, to understand their structure constants. Can you all hear me? Am I? Yeah. And they were defined recursively, and it's not even from that clear that they have no negative coefficients. But later on, there came explicit formulas summing over combinatorial objects, and some of these I'll talk about RC graphs or Pipedreams. So this is a model of Bergeron and Billy, and there's other models using prism tableau, for example, and there's even models from Fermin and Kirillov, and there's some recent ones called bumpless Pipedreams by Lamley and Shimozono. And okay, but let's talk about the first one. Okay, so how do we understand all these polynomials? So what's an RC graph or reduced Pipedream? So you have the triangle, and you are going to tile it with these two tiles, so kind of crossings and these non-crossings. You label the wires on the left 1 up to n. And then when you tile in this way, the wires of a tiling create like a history of where these wires go, from the bottom to the top. And this creates a history of a permutation. And by convention, the permutation at the top, we call it W inverse. So in this case, the permutation this creates the permutation 1, 5, 3, 2, 4. So what you see on the top is the inverse of that permutation. Okay? And we say that the RC graph is reduced if the number of crossings is the length of the permutation. Okay, so in this case, the length is 4. Okay, and if it's reduced, then no two wires cross more than once. Okay. Any questions with what RC graph is? And then this model of Bergeron and Billy says that if you want to write a Schubert polynomial, you can sum over these reduced Pipedreams of the permutation W, and for each crossing, you write xi for wherever that row is. Okay, so for example, here are all the reduced Pipedreams of 1, 4, 3, 2. There's 5 of them. Oh yes, I think so this is, I think this is wrong. Yeah, it should be here. Yeah. So so I must have done, let me see what happened. Yeah, so yeah, I think I did a wrong move. This probably should be here. Sorry about that. So yeah, this should be changed. Okay, sorry about that. Thanks. So yeah, okay. So please ignore this, but they should be here. So there's two crossings here. So you have x2 squared, x3, this x1, x2 squared, x1, x2, x3, and well, because this should be here. And this is x1 squared, x3. Okay, sorry, and this would be, there's two crossings here. So yeah, sorry about that. Okay, but there's 5 of them. Okay. So we're going to study the principal specialization of these Schubert polynomials. Okay, and so let's see why this would be of interest. So, well, this just the formula we just saw. This would count reduced Pipedreams of the permutation W. So in particular for the permutation before, it's 5, and if you have a permutation that's 1 and then n plus 1 n, so if you just reverse everything else, the number of RC graphs is a Catalan number. So So it starts to get a bit interesting. But in general, for any permutation, this principal evaluation has this formula by MacDonald. That is, you take 1 over the length factorial, you sum over the reduced words of a permutation, and I'll review that in a second, and you multiply the indices of the reduced word. Okay, so it gives you kind of this like weighted sorting network, this specialization. This is true for any permutation. And this recently had a bijective proof by Billy, Holroyd, and Young that they go from RC graphs to like labeled sorting networks. Okay, so here's that second reason to study these principal specializations. Let's look at an example of this. So a reduced word of a permutation, A1 up to AL, are the indices of a reduced decomposition of the permutation into the product of adjacent transpositions, okay, SI. So for example, the permutation 1, 4, 3, 2, it has 2 reduced words, basically the 2 kind of break moves. So S2, S3, S2, or S3, S2, S3. So you would have, and then the, yeah, sorry. I should not. Okay, so this MacDonald identity says that if I multiply 2 times 3 times 2 plus 3 times 2 times 3, okay, so I have here 12 plus 18, 30, and I divide by 3 factorial, I get 5 before, okay? So in some sense, that maybe that's a way to compute a different way to compute the principal specialization if you don't want to do these RC graphs and do the mistakes I just did. But, okay. So maybe another reason is some special cases are interesting. So if the permutation avoids 3, 2, 1, so it means that if you look at the permutation matrix, you're not going to find a 3-term decreasing subsequence. Then it's the diagram of the permutation, which is what you obtain if you take the permutation matrix and you kind of plot these lines. So the diagram is what's left. In that case, the diagram, which is there in orange, is a diagram of a skew shape. So Billy, Jokush, and Stanley proved this in '93. Moreover, every skew shape you can obtain it from the diagram of a 3 to 1 avoiding permutation. So there's a way to kind of go back. And when you have a permutation that's 3 to 1 avoiding, all its reduced words are just related by commutations, not braid moves. So in that identity of MacDonald, you're just summing the same thing over and over again. So in that case, the principal specialization is just 1 over L factorial, the product of just any reduced word. And then the number of reduced words are actually in bijection with standard Young tableaux. So we saw what standard Young tableau was on the previous talk. So you get the number of standard Young tableau of a skew shape. So the evaluation in this case is it's a multiple of the number of skew standard Young tableau. So for example, for this particular permutation, the factorials and the reduced word cancel out, so you get the number of standard Young tableau, which is 61. So, I mean, this is a prime, so there's no hope that you're going to find any nice formula in general for this number of reduced words. Okay, and this is kind of the reason we kind of maybe we're interested in this is because we had this big project with Igor and Greta that's still maybe not finished, studying standard Young tableau of skew shapes. Okay, so maybe hopefully it's maybe.
How do you get from this orange to the skew tableau?
Yeah, so I guess maybe if you kind of if you remove the empty columns and rows, this is this. Oh,
it's a rotation.
Yeah, sorry, it's kind of reflected in. Yeah. Mm-hmm. And there's a way to get any skew shape you want. You can find the reduced word. Okay. But the reason kind of another reason to study these principal specializations is what motivated some conjectures. So it's a paper of Stanley called Schubert shenanigans or some Schubert shenanigans. So it's so he was studying so we'll hear more about this in the next talk. So by Kristen, so I won't say much, but he was looking at the weak order and the symmetric group, and a certain property called the strong Sperner property on the weak order, a conjectured property. And Stanley phrased the problem of proving this property of this poset by showing that a certain matrix of the principal specializations was invertible. Moreover, it had a really pretty determinant. And if you prove that, then it implied that property. And this was and this was settled by Christian, who's speaking next, and Yibo Gao, and maybe around the same, or roughly the same, up to a couple of weeks later, or also by Zach Hamaker, Pechenik, Speyer, and Weingart, and anyways, and this implied this property. But you'll hear more about that on the next talk. So maybe so Stanley was looking at this matrix of these principal specializations. So then he asked, well, how? I'm studying this matrix. How big and small are the entries? So first, how small can the principal specialization be? So from now on, I'm going to denote it mainly by by the symbol, okay, omega w. So it just means the number of RC graphs, the principal specialization. So how small can it be? Well, it's equal to 1 if and only if the permutation avoids another pattern of length 3, if it avoids 1, 3, 2. So if you cannot find a 3 by 3 matrix that has the same, if you cannot find a 3 by 3 minor that looks like the permutation matrix of 1, 3, 2. So that's well understood from, so what's the next value? So Stanley conjectured that it's equal to 2 if and only if the permutation contains the pattern 1, 3, 2 once. And this was proved by Anna Weingart and also by Greta around the same time. And Anna Weingart showed that actually the principal specialization of any permutation is bigger than or equal 1, and the number of occurrences of the pattern 1, 3, 2 in the permutation. And last year, Yibo Gao strengthened this result by showing that eventually, for any permutation, the principal specialization is at least 1 plus the number of 1, 3, 2, the occurrences of 1, 3, 2, and the number of occurrences of 1, 4, 3, 2. Okay, so this ends is just counting how many times you see this pattern on the permutation. Okay, but well, if what's an estimate of this? How many patterns you have? Well, I guess you have to pick and choose 3 entries and see if you have that pattern. So it's roughly n cubed, and this is n to the 4. So these are kind of polynomial bounds on this principal specialization.
So do you count twice? Like the second one gives you 3.
Yeah, I guess you would count. Yeah, twice. And then there's some, and Yibo Gao has some interesting conjectures of what's going on. So that's kind of on the small side, how lower bounds. But Stanley also asked, well, how large can the principal specialization be? That's more or less what we're going to concern for the rest of the talk. So let un, and I have it there, it's the maximum, if you look at all permutations of Sn, what's the maximum value of that principal specialization? Okay, that's un. And Stanley showed that the log base 2 of that maximum divided by n squared is between 1/4 and 1/2. Okay, and so we're all on the same page. Let's see why that's true. So there is this Koshi identity. I guess maybe you could think of it as kind of what we saw yesterday. Maybe in Damir's talk, like Burnside's identity, an analog of that. So that if you sum over 2 permutations, that when you multiply them, you get the permutation nn minus 1 all the way that goes all the way to 1. That's W0. If you multiply the principal specializations of those 2, you get 2 to the n, choose 2. So how can you get the result of Stanley? Well, that product there, that sum there, is less than or equal. It's bigger than or equal your maximum, right? Because, well, it's going to be much smaller, and then by taking logarithms and so on, you get the bound of 1/2. Okay, so that's the upper bound. And so again, so we're all on the same page. So to prove the lower bound, well, this is less than or equal the number of terms plus the maximum squared. And then the n factorial is not, you're looking at kind of exponents that are quadratic, so this doesn't really matter. And if you take in the square root here, you get the 1/4. Okay, but the proof is non-constructive. Right? It's just saying you're summing over this. And then I guess the sentence right after says that Stanley said there's probably a limit of this as n goes to infinity. Okay, so this it's not clear that there's a constant that this goes to a limit as n goes to infinity, but but that's the conjecture. Oh yeah, this should be n squared. Sorry. Yeah. Okay. I think it's corrected. Oh no. Well, I think eventually. Yeah. Okay, so this should be. Sorry, this should be. Sorry. So the conjecture is that there is a limit. Okay. See, I lost my voice, some twos and some double crossings. Okay. So what's maybe now more this is like an outline of what follows. So what's the progress on this conjecture? So it's not yet settled. So these are the non-constructive bounds of Stanley between 1/4 and 1/2. When we're in a paper studying skew standard tableau with Igor and Greta, we improved the lower bound to 0.25162. And Stanley had this to say on his website that we just kind of shaved a little bit off the lower bound. And I thought maybe that he was not doing justice to our lower bound, but that really is the way to round the lower bound. And then I'll talk about mainly this. I'll show you how this was obtained, but the best result we have is the following. So we have this lower bound that's an explicit and universal constant, but we actually conjecture that this is actually the actual value of the constant. So I'll explain how that's obtained. But we still, of course, don't have this. So if you try to improve the upper bounds, so Igor and Damir have this result that goes from 1/2 to 0.46, and I'll tell you how to improve that upper bound to 0.37. Okay? But this is what the actual value probably is. Okay? Any questions with, yes?
Question mark means the author of this thing are unknown?
Sorry. Oh yeah, so I'll reveal that, yes. Yeah, absolutely, yeah. Sorry, it's like a little, okay. Okay, so let's see how first we got that little improvement. So I told you that when the permutation avoids 3 to 1, there is a connection between the principal, specialization, and standard tableau of a skew shape. If the permutation avoids 2, 1, 4, 3, if those are called vexillary, then there is a shape lambda such that the principal evaluation is the number of semi-standard Young tableau of shape lambda with a flagged condition. So it means that we impose some conditions of how big the entries in a row can be. Okay? So one such example is 1432, that one that I had the mistake on. So if you apply this result, if you want to count the principal specialization here, it's the number of semi-standard Young tableau of shape 2, 1, and the shape you get it from the diagram. And then if you look at the diagram, this row here is on the row 2 of the partition is on the row 2 of the diagram. So you impose that the entries on the first row are less than or equal to. This second row of the partition is on the third row, so you impose this to be less than or equal 3. And there's 5 such semi-standard tableau. Okay? So it's another reason why that's 5. And if you take a staircase, so like the permutation that would give you a staircase, and you just kind of push it down C, if you have C fixed points at the beginning, 1, 2, 3 up to C, then by the same result, the number of the principal specialization is the number of semi-standard Young tableau of a staircase of size A, where every row is less than or equal C plus 1, C plus 2, and so on. And there's a really nice product formula by Proctor for this number of semi-standard Young tableau. So when C equals 1, you get the Catalan numbers, and in general, this is a determinant of Catalan numbers, but that's pretty, but what's useful for us is that it's a product. Okay, any questions? Okay. So on the top, you have the result from before. And now we ask the following question, well, for which A and C adding up to n is this principal specialization maximal? Okay, what's the sweet spot between the A and C? And with Igor and Greta, we found that when A is the size of the staircase is a third, then you attain your maximum. And moreover, if you take 1 over n squared and log base 2 of that product, that goes to as n goes to infinity, this goes to this constant 0.25162. Yes. For which number?
This 0.25.
Yeah, it goes from the asymptotics, which is a universal constant that comes from the asymptotics. Is that?
I mean, can you express it as your,
Um,
I don't know, whatever.
yeah, I think it came from the asymptotics here, but I'll have a for the strengthening. I'll have a similar. I'll tell you.
Yeah. Okay, that's more interesting.
Yeah, but. And that's the largest limit among all ratios. Okay, so that's just by looking at looking at this example, you can get they have large enough principal evaluations to improve the lower bound. Okay, so that's how this was obtained. But let's talk about this one. Okay, the next one, which is what we conjecture the actual value to be. Okay. Okay, so in Stanley's paper, but also in a paper 1 year before by Merzon and Smirnov, they looked at the following. So they looked, well, what permutation achieves the maximum principal specialization? Okay, so here you have the values, the maximums, and here you have the permutations that achieve that. It's not always unique. Do you see any patterns here, like anything, something you would conjecture, like? So the permutations that seem to be maximizing this have these runs. Okay, like 1, 3, 2, 7, 6, 4. Okay, so the conjecture that both authors did was that the maximum is achieved at a permutation that has these runs, and these permutations are called layered permutations. So let me explain what they are, but you can kind of see the pattern. So if you have a composition of n, b1 plus b2 plus bk equals n. A layered permutation is a permutation of size n that has runs of length bk, bk minus 1, and b1. So you have here a run of 2, run of 3, 2, a run of 5, and a run of 2. Okay? So they're indexed by these compositions of these lengths of runs. They're also called Richardson permutations or pop stack sortable permutations in the pattern avoidance community. So is it clear what these permutations are? Okay, great. Okay, so let's say that Ln is the set of layered permutations in Sn. So they have the ones that maximize the patterns the occurrences of 3 to 1 patterns, but I cannot give it to you as a permutation class. But I mean, yes, they are in this pop stack sortable, which is a generalization of pattern avoidance. So the conjecture is that for these ones, I guess, are the ones that maximize this evaluation. So now this is the original problem. What's the maximum evaluation of the overall permutations? What if we study a different problem? We focus on the layered ones, which appear to be the ones that are maximal. So that's Vn. So we show that there is indeed a limit if you restrict to layered permutations. And that limit is given by a universal constant. I'll explain where that comes from. And the maximum value of overlayered permutations is achieved at runs that follow a geometric progression given by some other universal constant. Okay, which is given by this. So for example, this is maybe one of the maximal layered permutations of, I think this is 30, size 30. And this is one of the maximum permutations of size 1,000. So these runs start following some geometric progression. So this is our main result. Any questions with? Okay. So yeah, I'll tell you. Yeah, I'll tell you where they come from. Okay. So because this is you're exhibiting a family. So this is at least an upper bound. At least a lower bound, but this is what we conjecture. If you believe this conjecture of Smirnov and of Stanley, this should be the actual value. Okay. Okay. So how? Let's go over sketch the proof. So if you have if your permutation is kind of the direct sum of two permutations v and w, then the principal value or the Schubert polynomials are just the product of the Schubert polynomials of v. And of w pushed by the size of v. So if you just add as many fixed points as the size of v. So just by from the definitions or even the RC graphs or whatever. So then the principal evaluations are the product of those two. Okay? We've seen before that if we take a staircase and or the permutation that gives us a staircase and we shift it with C fixed points, then the principal evaluation is this number of semi-standard Young tableau, which has this product formula by Proctor. So we're going to call it PCA for product for both Proctor and the fact that it's a product. So then in a layered permutation, you can start shaving off runs. So the principal evaluation of a layered permutation with k runs is just the Proctor formula. If you take if you just take the last run, okay, because you would this is the kind of the number of fixed points you would have, times the evaluation of the previous layered permutation. Okay, so we have this. We're going to use this. Okay. Any questions? So already. So this is what I just had before, Proctor's formula, and then this recursive way of computing the principal evaluation. So already you can here use like a dynamic program and find the best B1 that works. And if you do this, I showed you this table when you were doing UN, and you can kind of get stuck at n equals 10 if you do it kind of naively computing all the Schubert polynomials. If you restrict to Vn and you use a dynamic program, you can just go quite high. So this is like you can calculate 300 values and you can start seeing what sequence of runs is optimal and try to find these constants. Okay, but it's kind of converging slowly to this 0.29. But anyways, this is computationally. But let's try to turn this into a proof. Okay, so this is kind of this again. Just remind you that recursive way of taking one run at a time. Vn is just the maximum over all compositions that add up to n of the Richardson permutations. And then if you want to compute that maximum, first you could compute the first run, the maximum value of the first run, using kind of this dynamic program. Okay, of this product. And what we use is we're going to use very precise estimates for this Proctor's formula to find what's that maximum V1 and iterate. Okay. So here is let's take logs. So we have here the log of Proctor's formula. And here it's indexed by these kind of points ij on a triangle. So we're summing logs of this over this triangle. So this is where the constants are coming from. Okay? So the first thing is that you can find good bounds for the logarithm of this Proctor formula in terms of this function f, which is given here. Okay, so we had a permutation of size n. We shaved off. We removed a run of size m. So this function. So the function is a function of m over n, which is some value between 0 and 1. Okay, so where does this function come from? Well, this function comes from a double integral that approximates this logarithm of Proctor's formula. So what you have here is an illustration of here you have the points where you're adding this function. Okay, here's the function here, log of maybe at m equals 1 of these values. So this function is convex, and it's also constant on the diagonals where I plus j is constant. So adding over these black points is the same as adding over the centers of the squares. But now you're inside the triangle. And this function is convex, so the sum over the center of the square is less than or equal to the double integral of that function. And that's where the function pops up. The function is also decreasing, so that's how you get the upper bound. The function is also decreasing in the x and y direction. So if you instead of summing here, you sum over the centers of the squares, but to the right and up, then that's going to be less than or equal. The sum over these points of the centers here is going to be less than or equal, and then you can use some inequalities and to also obtain this kind of a similar double integral with different values, and that's how you obtain the lower bound. Okay, so that's where the function came from. And any questions on this? Okay, so that's maybe the first step. kind of analyzing this function, this formula of Proctor. Okay, so we can approximate the logarithm of this Proctor formula by basically n squared times this function, where the value of the function is between 0 and 1. And now we find the unique constant so that this fx, the function plus beta x squared has a unique maximum. So we're going to optimize that. Okay, so this function fx we saw before that came from this double integral has a unique maximum alpha between 0 and 1. And moreover, that maximum is so that the maximum value is beta. So we wanted to have a unique maximum, and we want alpha, and we want the maximum value to actually be beta. Okay? And so here we have the function f. Okay? And here we have the function fx plus beta x. And the maximum of this value is beta, which is 0.20 something. Okay? And here is the function that we need, the auxiliary function we need, so that we have a unique maximum, and the maximum value is actually beta. Okay, and then alpha is 0.4 something. Okay.
So the fact that there is a unique value, is that something you have to verify?
Yes, yeah.
Calculation, or
yeah.
You can anticipate that it will be the case?
Well, we verified and we set it up so that the actual max value is also beta. But I think I don't know if we could anticipate it, but yeah. Okay. Okay. So then we're almost done. So the next thing we need to show that the logarithm of this maximum over layered permutations minus that universal constant times n squared is less than or equal 4n. So that's going to get us so that's going to decay like we want. And moreover, if a layered permutation if the logarithm of the principal specialization of a layered permutation is within 4n of that beta n squared, then the composition of that layered permutation follows that geometric progression with the value of that maximum alpha. Okay, so this is the last sketch of a proof, and then we'll go over other things. So just bear with me 1 second. So for the upper bound, we again do this kind of dynamic program. We use induction, so we can assume that we have the upper bound for the smaller layered permutation. And then we can use the previous lemma with the pretty triangle, hopefully pretty, for the logarithm of Proctor's formula that involves this function f. And then the maximum value of fx plus beta x squared, well, that's exactly beta. Okay, so you get beta n squared plus 4n. And this is achieved when the value x is alpha. So the maximum is alpha, so the maximum value. So alpha, so the ratio between m and n, so the run you shave off, the ratio should be alpha. So therefore, the ratio of what's left over the whole size n should be alpha. Therefore, the first run should be roughly 1 minus alpha times n. I'll repeat this in a second. For the lower bound, for the lower bound, if for a layered permutation, this is bigger than or equal that actual value alpha plus Proctor's formula of what's left. Again, we use induction and the bound for the Proctor's formula. And we also now use the fact that beta has this property that fx plus beta x squared is beta, so we get beta. And I told you that alpha was 0.4 something, so in particular it's less than a half. So this 1 plus 2 alpha is at most 2. So this is at most 2. So we get the lower bound we want. Okay. So combining both things, we get the bound we want, and And the bound is attained when the run, P1, the first run, is proportional to 1 minus alpha over n. So this should be 1 minus alpha over n. So what's left is of size alpha n. So then the next run is going to be 1 minus alpha times this length. So you get 1 minus alpha alpha n. And then B3 is going to be 1 minus alpha times L alpha squared n, and so on. Okay, so you get that these runs satisfy this geometric sequence. Okay? Okay, that's the end of the sketch of the proof. Any questions? Okay, so remember, okay, the square is back. Okay, so this is Stanley conjectures is a limit for this maximal principal evaluation, and this is what the conjectured value should be, but at the moment it's just a lower bound. Okay, so now if you kind of maybe if you're stuck maybe trying to prove this, then can you try to improve upper bounds and see how close can you get them to the actual value? So Damir and Igor have this improvement, and let me tell you how this is obtained. So to review the next one, okay? But again, this is the value. So okay, so UN is the maximum value of the principal specialization over all permutations. Instead, we could look at the sum overall of the principal evaluation of all permutations of size n. Okay, so this is just the total number of reduced Pipedreams where we don't care what permutation we have on the top. Okay, and if you believe Stanley's conjecture, then that constant is the same as the constant you would get if you take the limit of the sum over n squared. Okay, and the reason for that is that the summing over all the overall principal evaluations is between the maximum and n factorial times the maximum, and again taking logarithms and so on, the constants have to be the same. Okay. So instead of kind of focusing on the maximum value, why don't we just look at the total sum of RC graphs and find the asymptotics of that? Okay, and building from this idea is how Damir and some geometric and some modularity. That's how Damir and Igor can improve the bound, and let's see how we can, by considering instead an, how you can improve it further. Okay. So here's a table of the total number of RC graphs as n grows. So for example, there's 2 here, and Ulrich, I think you can anticipate a question here. So here there's 8 diagrams, but there's 7. So there's one that has a double crossing. So which one shouldn't be here? That one. Okay, so there's 7. Okay, so I don't care anymore what the top permutation is. Okay. So is it clear what I'm counting now? Okay, so tilings with the property that they don't cross twice. Okay, so so we're interested in this problem, maybe not focusing so much where the maximum happens. And one observation is that this sequence is less than or equal term by term to this sequence. Do you recognize this sequence? So this is the number of alternating sign matrices, so n by n matrices with 0, 1s, and minus 1s, whose rows and columns add to 1, and the signs alternate. And maybe I think of work of last school, but this has maybe has a new proof by Anna Weingart. The total number of reduced RC graphs is less than or equal the number of alternating sign matrices. So therefore, one very good thing about alternating sign matrices is that they have a product formula. So we can study its asymptotics, and that's where the 0.37 comes from, just by taking log base 2 of that and dividing by n squared. Okay. So that's where the upper bound comes from. Any questions? So maybe we've seen some talks about the 6 vertex model. So let's see where this is. Let me just make an aside here of where this bound comes from. So another model, recent model for Schubert polynomials by Lam, Lee, and Shimozono is using these bumpless Pipedreams. So here we have basically the 6 vertex model. We have a tiling of the n by n board with these 6 tiles. And we have a condition that the wires start on the right and go to the bottom. And we say that a bumpless Pipedream is reduced if no 2 wires cross at most once. So here are the, remember for n equals 3, there were 7 RC graphs. So here are the 7 bumpless pipe dreams. So they gave a formula for Schubert polynomials using these bumpless pipe dreams. But we're just interested in the number. Okay? And here is an alternating sign matrix, and there's an encoding to a tiling with these 6 pieces. And when you do this correspondence, sometimes 2 wires cross. It's possible that wires cross more than once. So Anna Weigand showed how these bumpless pipe dreams that are not necessarily reduced are in byte correspondence with ASMs in a talk she gave at Fomin birthday conference last year. So that's how maybe one way of understanding this inequality. Okay, these count bumpless, reduced bumpless pipe dreams, and ASMs are in bijection with bumpless pipe dreams. Yes?
Maybe it's worth commenting that this bound 0.37 actually relies on the difficult result that ASM event is equal to the product. If I understand correctly.
So you, I guess, I mean, you can take this formula and then do some asymptotics on this formula, but you're saying that's hard?
The equality between the ASM event equal.
Oh yeah, that's very complicated. Yeah, that's a theorem of Zalberger and Cooperberg and highly non-trivial result. Yeah.
So I think it's interesting that this bound is sort of dependent.
Yeah, so this bound comes from some very interesting theorem that there's a book written about it, and it's a recent bijective proof, really like by Matej Konvalinka and Isla Fischer. Yeah.
I assume you could make a much more naive bound by just removing configurations where double crossing is local.
Well, this is what we did.
This is more or less what I guess what the bound that Damir and maybe I think you can explain what you want. But maybe but you're right. I mean, this is the ones that don't cross at all, and these ones can cross many times, and there should be some way of improving this somehow, but we don't know how. Yeah. So maybe any idea that it would help.
But you guys use usual pipe dreams, not the boundless ones, right?
That's true. They use yeah. So maybe there could be some. Yeah.
Yeah, because there are some empty spaces.
Okay, so maybe again some summary of these constants. So this is the conjectured value. At the moment, it's an upper bound, and if you try to go the other way, this is so far the best upper bound. But again, this should be the value. Okay, so there's a limit, and the conjecture of Merzon and Smirnov or Stanley is that the maximum happens at layered permutations, and even within our group, there's no consensus that this conjecture is true. But then if you believe the conjecture, or maybe for other reasons, then the maximum actually exists and it's equal to this. Or if you restrict to layered permutation, that's the maximum. Okay. So just to finish off, maybe let's look at a different problem. Very related problem. So Stanley's bounds, kind of effortless bounds, came from this Koshi identity. Right, where you kind of take the product of two principal specializations, but they're not the same permutation. It's not like the f lambda squared we like so much in Bernstein's identity. So, well, we could ask, well, I don't know, what is the maximum value of this sum? So U prime is the maximum value of this sum, the maximum permutation of this sum. Sorry, the maximum value, and here are the maximum values, and here are the permutations that attain them. And if you kind of so this is done very naively, but if you look at this permutation, it doesn't look layered, but it has this kind of weird kind of parabola support. So this is a picture, but okay. Can we maybe see this in a bigger scale? So is it clear what I'm doing here? What we're doing here? Okay. So this identity, this Koshi identity, comes from, it's a special case of a Koshi identity of double Schubert polynomials. So I think Paul mentioned double Schubert a little bit when these mu i's were not equal to 0. So in general, if you take a double Schubert polynomial, you can break it up as a sum of two products of single Schubert polynomials that multiply to the right permutation here. And it just so happens that when you have the reduced permutation, n minus 1 all the way to 1, this is just the product of xi plus yj over a triangle. So that's where that comes from, okay? And in this RC graph paper, Bergeron and Billy have a model for this identity using double RC graphs. So now you have kind of, you can duplicate your diagram, and you have again this, again you don't have wires, you don't want wires to cross more than once, and hopefully I didn't make a mistake here. But, and here are the 8 double RC graphs that explain that 2 to the 3 choose 2. So they said that if you kind of focus on if you look at the bottom part, you're going to get W. And if you look at the top part, you get U. Moreover, there's a way to get all RC graphs or double RC graphs of a permutation by starting with an initial configuration and doing 2 moves, and you can get to every other one. Okay? So you could use this to form a Markov chain and try to kind of get for bigger examples and get further down. So we did this. We set up a Markov chain in a. So any double RC graph can be generated by local moves. So we did this, and maybe for a couple billion of these moves, and this is maybe 50 by 50, and then this is. I'm not certain this is completely mixed, but this is how far I'm not certain at all that this is completely mixed, but after 5 billion moves, this is what you get. And if you focus on the permutation that this RC graph, bottom RC graph is giving, it seems to look like this, which, well, it's not contradicting this example from n equals 10. But we have no other tools or anything. But so any ideas that you have would be welcome. But it's asking a different problem, a different question. Okay, so.
What is the question?
Well, the question is, I guess, what's the permutation? So when you just focus when you focus on just a single specialization, you want to know what permutation maximizes it, and it seems to be these layered permutations. And here, if the question is, what W maximizes this sum? And but there's no, we're unclear what it is, but just it seems to be there seems to be some different pattern, but not clear. Okay, so just a summary of the bounds, and yeah, thank you very much.